Consider where the electricity actually comes from. The simple answer is a power generating station, also known as a power plant, usually someplace far away. But the reality is much more complicated than that. Generation is only the first of many steps our power takes on its nearly instantaneous journey from production to consumption. The behavior of electricity doesn't always follow our intuitions, which means the challenges associated with constructing, operating, and maintaining the power grid are often complicated and sometimes unexpected. Many of those challenges are overcome at a facility which, at first glance, often looks like a chaotic and dangerous mess of wires and equipment, but which actually serves a number of essential roles in our electrical grid. As simple as it is to imagine, the power grid isn't just an interconnected series of wires to which all power producers and users collectively connect. In reality, the electricity normally makes its way through a series of discrete steps on the grid, normally divided into three parts: generation, or production of electricity; transmission, or moving that electricity from centralized plants to populated areas; and distribution, or delivering the electricity to every individual customer. If you consider the power grid a gigantic machine, and many do, substations are the linkages that connect the various components together. One of the cool parts about our electrical infrastructure is that most of it's out in the open, so anyone can have a look. I'm somewhat of an infrastructure tourist, a regular beholder of the constructed environment, and my goal is for you to be able to mentally untangle this maze of modern electrical engineering so that the next time you feast your eyes on a substation, you'll be able to appreciate it as much as I do. Originally named for smaller power plants that were converted for other purposes, substation is now a general term for a facility that can serve a wide variety of critical roles on the power grid. Those roles depend on which parts of the electrical grid are being connected together, and the types, number, and reliability requirements of the eventual customers downstream. And the first and often simplest of these roles is switching. The general layout of a substation consists of some number of electric lines, called conductors if you want to fit in with the electrical engineers, coming into the facility. These high-voltage conductors connect to a series of some or many pieces of equipment before heading out to their next step in the power grid. As a junction point in the grid, a substation often serves as the termination of many individual power lines. This creates redundancy, making sure that the substation stays energized even if one transmission line goes down. But it also creates complexity. The connections to these various devices are called buses, often rigid overhead conductors that run along the entire substation. The arrangement of the bus is a critical part of the design of any substation because it can have a major impact on the overall reliability. Like all equipment, substations occasionally have malfunctions or things that simply require regular maintenance. To avoid shutting down the entire substation, we need switches that can isolate equipment, transfer load, and control the flow of electricity along the bus. This may seem obvious, but turning on and off high voltage lines isn't as simple as flipping a light switch. At high voltages, even air can act like a conductor, which means even if you create a break in the line, electricity can continue flowing in a phenomenon known as an arc. Not only does arcing defeat the purpose of the switch, it is incredibly dangerous and damaging to equipment. So switching in a substation is a carefully controlled procedure with specially designed equipment to handle high voltages. Disconnect switches are often just called switchgear, in addition to the equipment that serves another important role in a substation: protection. I mentioned earlier that much of our electrical infrastructure is exposed and out in the open. That's nice for people like me who enjoy having a look, but it also means being vulnerable to an endless number of things that can go wrong. From lightning strikes to rogue tree limbs, windstorms to squirrels, grid operators contend with so many threats to their infrastructure on a day-by-day basis. When something causes a short circuit on the power grid, also called a fault, it can severely damage power lines and other equipment. Not only that, because of the overwhelming complexity of the power grid, faults can and do cascade in unexpected and sometimes uncontrollable ways, leaving huge populations without power for hours or days. Many of the ways we protect equipment from faults are handled at a substation. One of the most common types of electrical fault is a short circuit to ground. This type of fault creates a low resistance path for current to flow and leads to an overload of power lines and equipment. The simplest way to protect against this type of fault is with a fuse, a device that physically burns out at a certain current threshold. Fuses are dead simple and don't require much maintenance, but they do have some disadvantages too. They're one-time use, and they can't be used to interrupt current for other types of faults. On the other hand, circuit breakers are a class of device that serve similar roles as fuses, but provide more sophistication for dealing with a wide variety of faults. Like disconnect switches, circuit breakers need to be carefully designed to interrupt huge voltages and currents without damage. As soon as contacts within a circuit breaker are moved apart from one another, an electrical arc forms. This arc needs to be extinguished as quickly as possible to prevent damage to the breaker or unsafe conditions for workers. Extinguishing the arc is accomplished by a material called dielectric that doesn't conduct electricity. For lower voltages, the circuit breakers can be located in a sealed container under vacuum to avoid electricity conducting in the air between the contacts. For higher voltage, breakers are often submerged in tanks filled with non-conductive oil or dense dielectric gas. These breakers give grid operators more control about how and when current gets interrupted. Not every fault is the same, and sometimes operators even know about a disturbance ahead of time and can trigger breakers early to prevent cascading failures. Many faults are temporary, like lightning strikes or swaying tree branches. A special kind of circuit breaker, called a recloser, can interrupt current for a short period of time and re-energize the line to test if the fault has cleared. Reclosers usually trip and reclose a few times depending on their programming before deciding that a fault is permanent and locking out. If electricity demand on the grid gets so high that it can't be met by the utility, substations may also be used to shed load. Rolling blackouts are used to lower the total electrical demand to avoid bigger failures on the grid. One of the most important parts on the power grid is that different segments flow at different voltages. Voltage is a measure of electrical potential, somewhat equivalent to the pressure of a fluid in a pipe. At large power plants, electricity is produced at a somewhat low voltage of around 10 to 30 kilovolts, or kV. From there, the voltages increase much higher so that it can travel along transmission lines. Using a higher voltage reduces the losses along the way, making them more efficient, but also much more dangerous. This is why overhead transmission lines are so tall, to keep them out of the way of trees and human activities. But when transmission lines reach the populated areas which they serve, it's not feasible to keep them so high in the air. So prior to distribution, the voltage of the grid needs to be brought back down using transformers located within a substation. A transformer is an extremely simple device that relies on the alternating current of the grid to function. It consists of two adjacent coils of wire. As the voltage in one coil changes, it creates a magnetic field. This field couples with the other coil, inducing a voltage. The incredible part of a transformer has to do with the number of loops in each coil. The induced voltage will be a function of the ratio of the loops. For example, if the transmission side of a transformer has 1,000 loops, while the distribution side has 100, the voltage on the distribution side will be 10 times less. This simple but incredible fact makes it possible for us to step up or down voltage as necessary to balance the safety and efficiency along each part of the power grid. The simplicity of transformers is great in a lot of ways, but it also means it can be difficult to make fine adjustments to the power leaving the substation. Because of this, many substations include equipment for monitoring and controlling the power on the grid. Instrument transformers are small transformers used to measure the voltage or current on the grid or provide power to system monitoring devices. Depending on the varying transmission and distribution losses, the voltage on the grid can also swing outside an acceptable range. Regulators are devices with multiple taps that can make small adjustments up or down to the distribution voltage on feeder lines leaving the substation toward customers. If you look closely, you can sometimes see the regulator dial indicating the tap position. All that different equipment requires lots of maintenance. The final and most important role of a substation is that it be safe for electricians and linemen to inspect, repair, and replace equipment. Substations are usually the only locations where extra high voltage power lines get close to the ground, so safety is absolutely critical. The buswork running along the substation is protected from short circuit by large insulators to avoid arcs to ground. Even the connections into each piece of equipment are done through a device called a bushing, which maintains a safe distance between energized lines and the grounded metal housings. Some substations have large concrete walls to serve as fire barriers between equipment. All substations are built with a grid of grounding rods and conductors buried below the surface. In the event of a fault, the substation needs to be able to sink lots of current into the ground to trip the breakers as quickly as possible. The grounded grid also makes sure that the entire substation and all its equipment are kept at the same voltage level, called an equipotential, so that touching any piece of equipment doesn't create a flow of electricity through a person. Finally, substations are surrounded by In many ways, the grid is a one-size-fits-all system, a gigantic machine to which we all connect, spinning in perfect synchrony across, in some cases, an entire continent. On the other hand, our electricity needs, including when we need it, how much we need, and how reliably it should be delivered, vary widely. Power requirements are vastly different between a sensitive research facility and a suburban residential neighborhood, between a military base and a country club golf course, and between a steel mill and a bowling alley. Likewise, every electrical substation is customized to meet the needs of the infrastructure it links together. As the grid gets smarter, as demand patterns change, and as we hopefully continue to replace fossil fuel generation with sources of renewable energy to curb global warming, managing our electrical infrastructure will only get more challenging. So substations will continue to play a critical role in controlling and protecting the power grid.